Okay, so today I'll be talking about problem 7.2. It begins by giving us two diagrams shown at the top labeled as A and B. And the first question is going to ask us what the charge on the capacitor as well as the current through the resistor with respect to time is. And this one is regarding figure A. So to begin with, we're going to start off with our pretty straightforward identity equations. So V equals Q over C as well as V equals IR. Except specifying that this is for the capacitor and this one's going to be for the resistor. And then also current is going to be the change in charge over the change in time, seeing as this is the only difference. This is going to be the only current running through the resistor in this figure anyways. So to start off, we can start by with the equation of the potentials. The added potentials is going to be equal to 0. Substituting in these equations for these variables, we'll find that Q over C plus R times dQ dt equals 0. So this is going to be IR, except substituting dQ dt for I. Moving up here, we can simplify or reorganize the equation to show us that dQ dt is going to equal negative Q over RC. We can then move the dt over to the right side and integrate both sides. So we'll have the integral of 1 over q dq equals the integral of negative 1 over rc dt. This is going to yield ln of q equals negative t over rc plus c naught. This could be any letter. I just use c naught as a constant, seeing as it's usually plus c, but c is already being used. So this is going to be how we can find q. But to find this constant, we can set q of t to be equal to 0. And then we will then find that we're going to have c naught times e to the 0 is going to be c times the voltage of the capacitor. And then after a little bit more algebra and manipulation, we can find that q of t is going to be equal to C, the capacitance, times the electric potential, times e to the negative t over RC. And then current is just as we stated up here, is going to be the derivative of Q of t with respect to time, obviously. And this is just going to, I won't bore you with the algebra or the derivative, but it's going to come out to be V sub C over R equals e to the negative t divided by RC. So part B is going to ask for a few things. It's going to ask for the original energy in the capacitor, and it's going to ask us to integrate. Actually, this one is only one. My apologies. So this one is going to ask for the original energy in the capacitor and to integrate equation 7.7 to confirm that the heat delivered to the resistor is going to be the energy lost in the capacitor. So equation 7.7 is right here. P equals VI, or P equals I squared R. So we can use what we determined from I up here, down here, and we can find that P equals I squared R is going to be P equals V naught over R times e to the negative t over RC, that quantity squared times R. When we square this out and multiply by R, we will finish with this right here. So then we can go back to the formula dW equals P dt. And if we integrate both sides, we'll have W equals the integral of P with respect to time. Again, I won't bore you with the whole process of the integral, but if we expand this out, plug this in here for P, and our bounds are going to be from 0 to infinity because there's no time limit. We will finish with the idea that W, or the work, is going to be 1/2 V naught squared times C. All right, so moving on to part C and D. All right, so part C wants us to find the new QT and the new IT. So this is, I probably should have specified this earlier, but this is now looking at the figure B. So again, start with our identity equations. And this time we're going to add all three of them being the capacitor, the resistor, and the battery. Their sum is going to be equal to 0. So the capacitor and the resistor are both going to be negative, while the battery is going to be positive. So again, through some algebra and simplification, we will come out to dq dt equals I over RC times C V naught minus Q. Again, we move the dt to this side, and this time we're going to move the C V naught minus Q to this side, so that way we can integrate with respect to Q over here and integrate with respect to T over here. And then here I also multiply by -1, but I initially forgot to write that here and here. So this is going to be Q minus CV naught as instead of CV naught minus Q to account for the negative. This is just for ease later with the negative T to the R, e to the negative T over RC. But so we're going to have Q minus CV naught equals C naught times e to the negative t. Oh, I probably should have specified. These integrals are going to simplify out to ln of Q minus C V naught equals negative t over RC plus, again, some constant. And then this is going to simplify if we look at Q specifically. If we look at Q specifically, we will find that, and as well as put both sides to the power of e, we will find that Q equals CV naught plus C naught e to the negative t over RC. So again, we need to find out what this constant is. So we start by plugging in Q of 0, which is going to equal to 0. I initially forgot to write that. But CV naught plus C naught, we can simplify to C naught is going to equal negative C times V naught, again, capacitance and voltage of the battery. And then, plugging this in for C naught up here, we will find that Q of T is going to equal CV naught minus CV naught times e to the negative t over RC. I'm also just realizing that we could actually simplify this to be CV naught times 1 minus this e. But regardless, again, I of t is going to be the derivative, which again, I won't bore you with showing the derivation, but it's going to simplify out to V naught over R times e to the negative t divided by RC. So part D asks for a few things. We're going to be looking for energy output of the battery, which it gives us a little equation to go with here. It's going to ask us for heat delivered to the resistor and energy in the capacitor. So beginning with the battery, it gives us this integral right here to start with. So we're going to go from 0 to infinity, because again, there's no limit on time. And we're going to have V naught times I of t dt. So we just pulled a new I of t. We just pulled a new I of t in the last part. So we can plug that in here. And we'll have the integral of this equation, which is going to return this. And again, this integral right here is going to just be 0 minus 1. So we end up with negative C V naught times 0 minus 1. And we're going to find that the work is going to be C times V naught. I think I forgot to explain that in the last one of the previous parts. Yeah, down here. It's going to be the same thing as part B. But regardless, the resistor is going to be the same as the last circuit. There's no difference between these two. And so we can use the same equation there. And the capacitor, we are also going to use the same equation as the previous parts. So both of these are going to be 1/2 V naught squared C, making it so that both the resistor and the capacitor take half of the work of the battery. And that is all. Thank you, and let me know if there's anything wrong or needing further explanation.